Hi, I'm Dane Quinn from University of Akron, and today's video lecture will be an example dealing with planar kinematics. So we have a mechanism here, commonly referred to as a slider crank, and here link AO, so this link of length 2, rotates with angular velocity omega k. And I would like to find the velocity of the slider over here at B as a function of this input angle theta. So we will begin by defining coordinates and directions that will allow us to describe the configuration of this linkage. And we'll start off with directions fixed in the ground, I and j. And then here we have the input angle theta for this link OA. And let's define directions that are fixed in this link. And we'll call those I2 and J2 that are oriented with the angle theta with respect to I and J. Then let's define this angle as phi and directions I3 and J3 fixed in link AB, or link 3. Finally, the displacement of the slider we will identify with a coordinate x. So x measures the distance between O and B. Notice that A and O are a fixed length apart, L2. A and B are a fixed length apart, L3. And then the vector from O to B changes its length, but the direction is constant, so it only moves in the I direction. So with respect to these angles theta and phi, I can identify I2 and J2 and I3 and J3 in the following way. So I2 is cosine of theta in the I direction plus sine of theta in the J direction, while J2 is minus sine of theta in the I direction plus cosine of theta in the J direction. Then I3 and J3 can be written in terms of I and J as cosine of phi in the I direction, now minus sine of phi in the J direction. Here theta is a counterclockwise angle and phi is positive in the clockwise direction, while J3 is sine of phi in the I direction plus cosine of phi in the J direction. So we are able to relate these different sets of directions back to I and J. So now if I want to look at the motion and the kinematics of this linkage, it's useful to note the constraints. Link OA has fixed length L2, link AB has fixed length L3, and then again B is constrained to move only in the I direction. So we can identify what we refer to as a loop closure equation. So in particular, the vector from O to A, so that's R of A with respect to O, plus the vector from A to B, and that is the position of B with respect to A, is always equal to the position of B with respect to O. Or we can write R of B with respect to O is R of A with respect to O plus R of B with respect to A. And again, as this linkage changes its configuration, this vector equation is always satisfied. So now, in terms of the coordinates that we have identified previously, we have x in the I direction, that's the position of B with respect to O, is equal to L2 in the I2 direction, that's the position of A with respect to O, plus L3 in the I3 direction. And of course, I can write I2 and I3 in terms of I and J. So we have L2 cosine of theta plus L3 cosine of phi in the I direction plus L2 sine of theta minus L3 sine of phi in the j direction, and that must be equal to x in the I direction. Now notice that we want to solve for the velocity in terms of theta, but in order to do that, we'll need to find this distance x and this angle phi, and we can do that from this equation. So taking components in the I and j direction, we have two equations, and so I can solve for x and phi in terms of theta. In the I direction, we find that x is equal to L2 cosine of theta plus L3 cosine of phi, and in the j direction, 0 is L2 sine of theta minus L3 sine of phi. So notice that the second equation, I can solve for sine of phi in terms of sine of theta, or effectively phi in terms of theta, and I find that sine of phi is equal to L2 sine of theta divided by L3. And then I can use that back in this expression to solve for x. So with a little bit of algebra, we find that x is equal to, well, from the equation directly, L2 cosine theta plus L3 cosine of phi, but this reduces to L2 cosine of theta plus, and then again with some algebra we can use the fact that cosine squared is 1 minus sine squared, and we have an expression for sine of phi, so we can substitute in for this cosine of phi term, and ultimately we find L3 squared minus L2 squared, and then sine of theta squared. So we're able to solve for x in terms of theta, and we also have phi in terms of theta. Right, so we'll just make a little note. Both x and phi are found in terms of theta. And theta is the input angle. So again, the problem asked us to find the velocity of the slider as a function of theta. Now we'll turn to the velocity. Again, here's our linkage once again, and we had the angle theta defined, we had the angle phi also identified as this angle, and then we had x as the position of B, or the distance between B and O. Now I'd like to find the velocities. So in particular, the velocity of B, which is what I've been asked for, I can relate that to the velocity of A because both A and B are fixed in link 3. So the velocity of B is the velocity of A plus the angular velocity of link 3 cross r of B with respect to A. And then notice that A and O are both fixed in link 2. So I can write the velocity of A as the velocity of O, which is 0, plus the angular velocity of link 2 cross r of A with respect to O. Again, the velocity of O is 0. In terms of the coordinates that we've defined, the angular velocity of link 3 is minus phi dot in the k direction, while the angular velocity of link 2 is theta dot in the k direction. Notice that if theta dot is positive, link 2 is rotating counterclockwise, so that's in the plus k direction, while if phi dot is positive, then link 3 is rotating in the clockwise direction, which is in the minus k direction. Right, so that's where this minus sign comes from. So now using this expression for the velocity of A in this expression for the velocity of B, we find that the velocity of B is omega 2 cross r a with respect to O plus omega 3 cross position of B with respect to A. So finally, in terms of the coordinates, we get the following. The velocity of B is x dot in the I direction, and that's going to be this expression, which is theta dot k cross L2 I2. That was the position of A with respect to O, plus minus phi dot in the k direction cross L3 I3. And so this reduces to k cross I2 is J2, so we have L2 theta dot J2. K cross I3 is J3, so we end up with minus L3 phi dot in the J3 direction. Now, recall from the problem statement, theta dot was omega I. Let's go back and look at that. So the angular velocity was omega I input in the k direction, and in terms of the coordinates, the angular velocity of length 2 is theta dot k. So theta dot is simply omega I. And we've already solved for theta and phi. Well, we solved for phi in terms of theta. So now I can write this as L2 omega I in the J2 direction, which is minus sine I plus cosine J, minus L3 phi dot. And at this point I don't know what phi dot is, and I don't know what x dot is. But J3 is sine of phi in the I direction plus cosine of phi in the J direction. Remember, I've already solved for phi in terms of theta, right? So I don't have to necessarily plug that expression in for sine and cosine. I'll just leave them like this for now. So collecting terms in the I and J directions, we have minus L2 omega I sine theta minus L3 phi dot sine of phi in the I direction, and then in the J direction I have L2 omega I, that's the input angular velocity, and finally L3 phi dot cosine of phi in the J direction. So my unknowns, let's go ahead and fill in the left hand side, x dot I. My unknowns are x dot and phi dot. And I have two equations, right, to go along with these two unknowns. So I can simply solve these. In particular, taking components in the I direction. Let's go back and look at this. We have the I component on the left-hand side is equal to the I component on the right-hand side. So that gives me x dot equals minus L2 omega I sine of theta minus L3 phi dot sine of phi, and in the J direction I have 0 is L2 omega I cosine of theta minus L3 phi dot cosine of phi. So from the second equation I can solve for phi dot, and then I can use that back in the I direction equation to solve for theta dot. So doing that, phi dot is equal to L2 cosine of theta divided by cosine of phi times omega I. And finally, x dot is minus L2 omega times sine minus L3 times phi dot, which is, again, L2 cosine theta divided by cosine of phi times omega sub I times sine of phi. So we can actually manipulate this a little bit to come up with a couple of different expressions. Right? In particular, let's clear the denominator and write this as a simple fraction. And we have minus L2 times sine of theta cosine of phi from here plus cosine of theta sine of phi divided by cosine of phi times omega I. And so again, I'm doing a lot of algebra very quickly. If you would like, you can pause this and try to work all this out. But like I said, I'll just sort of show you the results from all of this. So this is one expression we can find. And in particular, the numerator is actually one of these sort of double angle formulas. You may or may not recognize this, but we end up with L2 times sine of theta plus phi divided by cosine of phi times omega I. So that's the speed of block B. A couple of important things. Clearly, both angles are important in this expression, but this is also linear in the input speed. So if I double the speed of link 2, let's go back and look at the picture here. So if this link spins twice as fast, then the block moves twice as fast. Again, the speed of the block is proportional to the input speed of the link. Now I can also take this and I can actually express this in terms of simply the angle theta. Notice that really this last term becomes tangent of phi. So if I go through and I do all the algebra, I make use of these expressions for sine and cosine, we end up with the following. Minus L2 times sine of theta 1 plus L2 cosine of theta divided by, and then we have this expression L3 squared minus L2 squared sine squared, all multiplied by the input angular speed. So again, there's a lot of algebra that goes into this, and if you like, you can pause the video right now and try to work that through. But these are three different ways of expressing, finally, the speed of the block in terms of the input speed of the link. So that's a pretty nice kinematics example, planar kinematics, and we've used the loop closure equation, so this equation that sort of describes the mechanism itself, together with expressions for the velocity of 2 points that are fixed in an object. So we use A and B fixed in link 3, and we use O and A fixed in link 2. So that's it. Thank you very much, and I will be back with more examples.